All right, so we're going to be in 6.4. We're going to start talking about logarithmic functions today. Most of you did this in Algebra 2, so it should be somewhat of a review. If you didn't do it in Algebra 2, hey, it's not that hard. So the key thing to remember, when I say it's not that hard, I'm not a really good judge. It's a logarithm is an exponent. That's the name of the game. A logarithm is an exponent. Okay, so we're going to start by rewrite the log function as an exponential function. One of the key things with math is a lot of times when we learn something new, we try to make it look like something we already know about. We've already talked about exponential stuff, so what we're going to do as we're learning logs is take the logarithm and turn it into an exponential. Then we'll go the other direction and turn the exponentials into logs. There's advantages to having it in an exponential form for certain problems and advantages to having it in log form for other problems. So being able to bounce back and forth between them is a pretty essential skill to make your life easier as far as when you go to solve equations. That's the idea. The whole reason we'll do most anything we do here is to solve equations in the end. So first example, this is kind of the learning example. Log base 3 of x. Okay, so we read this: y is equal to log base 3 of x. Okay, if we're going to rewrite that as an exponential, what you got to remember is the log is an exponent. So whatever that logarithm is equal to is the exponent. And when we're talking about exponential things, the base is the base. It's the big number that has the exponent, right? So when we read that, it's log base 3. The base 3. That means 3 becomes your base. The logarithm is equal to an exponent. That's what that statement up there says. A logarithm is an exponent. So whatever this is equal to is the exponent. So y is the exponent in this problem, and x is what it's equal to. Okay? Base is here. Exponent's what it's equal to. And then whatever's left over is what the exponential equals. Okay? So we're not doing anything with that yet. We're just rewriting it. We're going to get to where we do something with that eventually in this. Yes, yeah, today we will. But log base 2 of x equals 3. So rewriting this as an exponential. The base, this is log base 2 of x is equal to 3. The base is 2. The exponent is x or 3? 3, because that's what the log is equal to. So 2 to the third equals x. That's right.
And the base is coefficient, and then what it's equal to is the exponent.
Equal to is the exponent. The base is the base of the log. Right now we are. We're going to eventually solve equations with these. We're just rewriting them. We're taking the pieces and putting them in the right spot. Yeah, we would, when we go to solve the equations, yeah, that becomes x equals 8. Yeah, when we solve it. But right here, we're just rewriting is all we're trying to do. Try this one. Log base 5, 1/25 equals x. What's the base? 5. What's the exponent? What's it equal to? Now that looks a lot like the problems that we did on the quiz or yesterday, right? So that's the idea, that we've got a log equation. We can change it into an exponential equation if it works well. This one would work well with that to solve it. We could solve that by making that 5 to the negative 2 and work that out. The idea right now, though, is just rewrite them. here's the kicker. Ln, that's called natural log. Haven't seen that before. Natural log of x is equal to y. Okay. Does anybody remember what natural log is from Algebra 2? Yeah, it's really log base e is really what it stands for. It's a common log. It's used enough that in science classes usually is where you see that a lot. It's used enough that it has its own symbol. It's kind of like pi. Today's Pi Day. It's used enough they made its own symbol. Natural log base e is used enough in the work you do that they said, well, we're going to make it Ln. Give it its own little button on the calculator. They had a ceremony for it. Here's your button on the calculator. Anyway, so it's log base e. So rewriting that as an exponential.
So have you gone from natural log base to?
Well, you don't have to go and show every step in there. What I want you to understand is if you see natural log, no, it's this. It's log base e is what it is. So if we go to exponential, it's e to the y equals x. And you've rewritten it as an exponential. E to the y equals x. So natural log is log base e. Let's do this one. Here's another common log. They don't have anything written here. What base is our number system that we use? 10. We're a base 10 number system in our society. Base 10 number system meaning that 10 to the 0 power is the 1's digit, 10 to the first power is the 10's digit, 10 to the second power is the 100's digit. So you look at a number, it's base 10. So log with nothing written there, it's an understood log base 10. Good job, Katie. That's right. That this is log base. Anytime they have a log and don't have anything written there, it's a 10. Because our number system is base 10. Is what we're dealing with. If you're dealing with binary code, that's base what? Does anybody know? Binary? 2, yeah, base 2. That's Braille. Yeah, binary is base 2 because it's 1 or 0 is only 2 positions. Hexadecimal is another way, and that's base 6. And so that the way the number systems are work that way. There's different number systems. We work off the base 10 number system for the most part in our world. The binary system is electronics and computers. Hexadecimal is actually some computer stuff too. So. What?
Like the number under the log.
That's your base.
Yeah, I get that, but
that's all you need to get. There's when we start solving these equations, I think it'll start, clicking to you, what the use of it is, because you're not really using it right now. You're just rearranging things. Let's rearrange a little bit more, and then we're going to actually do some work here. So write the exponential as a log. Well, 3 to the x equals 27. So we're not solving this equation. We're rewriting it as a logarithmic equation. Okay. So what's the base on the side that's got the exponent? 3. So when we rewrite it as a log, it's log base 3. That's it. Whatever the exponent is, that's what the log is equal to. And then whatever the exponential is equal to is what you're taking the log of. Ten to the x plus 1 power is equal to y. Megan, you said log base 10 of y. No, but you won't see it written that way. Like, if it's a multiple choice type selection, you won't see it right. Log base 10, they'll just write it. I'm not going to count off for it, no.
But you know that's right.
Just so that you're used to, yeah, because you're never going to see a book write log base 10 or a test document write log base 10. I'm gonna try not to write log base 10 when I do it. I think it, but I don't write it. Let's do log base, or whoops, I almost read the answer. Got in a hurry. Brain's working them before I write them down. 8 to the 4th is equal to 24.
Log base A.
Okay,
No, log base.
you were right the first time. Mm. Yeah. Whatever the exponent is what the whole thing's equal to. The base in the exponential is the base in the log.
You're talking backwards.
Just read it backwards, read the bottom, then read the top.
Okay.
The base is A, so I'm saying the same words. The base is
I
A.
know, but like.
The exponent's 4.
Exponent's 4.
What is equal, of 24. Log base A of 24 is equal to the exponent of 4.
Is what it equals.
5 to the x is equal to 625. What's the base of the log base that we're using? Log base 5 of 625.
You better not write it down.
Oh, yeah. Yeah, let's do that. E to the square root of x is equal to y. So you use natural log of y. Again, you're not going to see them write log base e. They're going to write natural log. So that's why I don't write. You think that's log base e, but it's natural log. So you're not going to see them write that. All right, so we're going to work on evaluating some logs. I'm going to try not to use a calculator at all. So that it helps us understand the relationship between exponentials and logarithms. Some of them you can. If I want an exact answer, I can't always do that. So being able to do the ones that do work out nice without a calculator will help you be able to do the ones that will work out horribly without a calculator. Okay? Huh? Well, I'm going to try to help you where you don't need it as much. Log base 2 of 16 is equal to x. Now, yes, you can type in log base 2 of 16 in your calculator and it'll work it out. I'm not going to show you how to do that yet. But, or you may already know how. If you had Algebra 2, you should have. But what I want you to think about is how can I evaluate this without that? Yeah, that's exactly right. 2 to the x. Yep. X equals 4. So that means log base 2 of 16 is 4. So it's using the same skills that we did the last 2 days. It's nothing. Yeah, amazing. Who knew that math was a All right, so let's say we're taking log base 4 of 164, and they just write it that way. They don't put it equal to anything. I put the first one equal to x on purpose so that you think about it that way. Here, we've got log base 4 of 1 over 64, and we want to evaluate that. We're trying to do it without a calculator. So what I'm thinking is, oh, if I do it like I did example K, and I just say, oh, that equals X, because I don't know what it equals yet, then I can do it exactly the same way we did this example K.
So if it doesn't have something, it's equal to X.
Yeah, because if you're just evaluating, you don't know what it's equal to, put it equal to X or some other letter. You can pick your favorite letter. I don't know what. I don't know. I don't really have a favorite letter. X I use a lot, but so that would be 4 to the X equals 1 over 64. That would be one way to do that. So X equals -3 then.
That was not one of the reasons.
It may be. If you got if that was the quiz question and you got -3, then yes, you did. It's amazing. Let's do another one. What are we on? M. And guys, y'all act like you're surprised that what we've learned before actually relates to what we're doing now. It's crazy. It's like he meant for us to learn this in order.
Well, actually, equals X.
Equal to X, so put it equal to some letter. It doesn't matter what letter. We're going to use X because all my X.
And then bring 9
And there we go. We've evaluated logs. So we don't really have to have a calculator to do some of these. Yeah. Do the factor tree? No, it's fine. I just do them in my head. I don't write them down anymore. Been doing them a while, so I'm pretty decent at it now. All right. This is my 10th year. I've been doing math since I was like 4. So.
Me too.
Actually, before then, but anyway. Yeah, you do math when you're 1 and 2. Just don't call it that. You call it counting. All right, so I'm required to show you this. Yeah, because it is. If you needed to evaluate something, you could evaluate it using a change of base formula, is what it's called. Log base x of y could be done with log base 10 of y over log base 10 of x, and it equals the same amount. Same thing here. You could use natural log of y over natural log of x, and it equals the same thing. At one point, we had calculators that didn't have nice log base things. And at a more ancient time, like when Coach Mack was in high school, they didn't have a calculator that had log buttons. They had tables in the back of the book, and the tables were built off of log base 10 stuff because we live in a base 10 number system is where we live. And so they would just have this table of all of these log base 10s of certain numbers, and you would have to find the 2 numbers you needed. So like if you did log base 2 of 14, you'd find log base 10 of 14 and log base 10 of 2, and then you would divide those 2 numbers. Yeah, it's an unfortunate way of doing things. We have an incredible computer in front of us now that does those sort of things. We don't usually have to have that, but it's handy to have in case your graphing calculator dies, because the scientifics usually don't have the log base buttons on them, just because it takes up quite a bit of memory for it to do that.
I have a question.
Okay.
Is that natural log?
Yes, the bottom one.
You change it.
I just changed it. Instead of using log base whatever, I'm using log base 10 or natural log. They will both equal the same thing when you do that ratio there.
My current computer's one better.
Okay, buy you small. That's It's in the contract. Money. Come on in, Mason. Kayla, they need you. They're going to poke you and let fluids run from your body.
I love giving blood. Like I save a life.
I do, but I don't do it here. I had a bad experience with them here. So. This was the needle. It was sticking out of my arm like that, and they had packed stuff around to hold it.
I've done my own blood before. It's supposed to go like that, though, isn't it?
Yeah.
You had a new guy, didn't you?
I hope they were new. So I don't do that anymore. All right. Here we go with the function part. F of x is equal to log base a of x.
Okay, what if like does give blood and then
They test. That's why they draw vials before they get vials of it for testing.
But I was having a lie because they didn't have
You can lie all you want to, but they're still going to test your blood. And if it shows up bad, they're going to dispose of it. And they're going to notify you that you lied.
Yeah, I took my own blood before, so I had to tell you my car.
That's not creepy at all.
Well, one of my friends went to school to be a phlebotomist, and she was teaching me how to do it in her living room, so I kind of just trained myself.
That's not creepy at all.
Wait, so what do they do if they don't need it? How do they get rid of it? No, you don't just throw it away. It's dangerous. Can you give it to a hobo?
Incinerate it.
They burn?
Yeah.
Really?
Medical waste is incinerated.
I bet you my cat would drink yours.
All right.
My dog.
You don't want that to happen. You can't end up with AIDS. So
Don't they already?
the domain of a logarithmic function is 0 to infinity, which means what kind of numbers can we take the log of?
All real numbers.
No. Positive numbers only. Okay.
Oh, that's what.
The range is from negative infinity to positive infinity. No matter what the base is. That's the thing I want you to understand here. Doesn't matter what log base we're dealing with. If we're dealing with log base 10, natural log base 2, it doesn't matter. It doesn't change this. The rules are still the same. Yes. Which is sweet because, we've had a lot of them. We can only take the logs of positive numbers. It doesn't matter what the base is. We can still only take the logs of positive numbers. That's going to be important when we're talking about functions. It's also going to be important when we start solving log equations.
So you're saying the A cannot be negative or the X cannot be negative?
What we're taking the log of cannot be negative. The base doesn't matter what number it is. This is always the case, that you can only take logs of positive numbers and go from there. All right. So maybe we need to write that down. We can never take a log of 0 or a negative number. That's important. Very important. Quite important when we're talking about solving later on. So first thing we're going to do, talk about functions. So we're going to state the domain and range. Here's our function, log base 2 of x plus 3. Okay, so this is not just log base 2 of x, it's log base 2 of x plus 3. So what we have to do when we're talking about a domain is think about, all right, generally the log domain is only of positive numbers. We're taking the log of x plus 3. What makes x plus 3 positive? It's a 2. Not that it matters. To do that, we take whatever's in what we're taking the log of and make it greater than 0 and solve it. That's going to help us with our domain. Because we need to be taking the log of what kind of number? A positive number.
So you can't have the
Not an equal to because we can't take the log of 0 either. X has to be greater than -3. So our domain, it can't be 0. So it's greater than 0. Not equal to 0, but greater than 0. From -3 to infinity. Our range is still from -infinity to positive infinity. That hasn't changed. No.
So the domain is just the log value, or the x value is
Whatever you're taking the log of, greater than 0.
and that's the x value.
That's the x values. That's telling you what x values work for the domain.
Oh.
Example O. F of x, log base 5, bunch. Yeah. 1 plus x over 1 minus x. Ooh.
But this is 8.
Famous last words.
What?
All right, so our domain, we're going to set this rational expression greater than 0. Remember, we had a problem on a quiz in the not too distant past that we had a rational expression greater than 0. Yeah. So when we do that, we got to think, okay, well, what x values don't work? A positive 1 won't work. And then what would get us 0 on the top? -1. So those are open circles. So we need to test some values here. So I'm going to pick -2. And I'm going to pick 0. I'm going to pick 2. And figure out what's going on. So I'm going to plug those in to this problem here. -2. So that'd be 1 minus 2, -1 over -3. Right? No, -1 over positive 3, which is -1/3. Is -1/3 greater than 0? No, so this area is false. So it's not part of the domain. Well, I plug a 0 in. 1 over 1, is that greater than 0?
Yes.
Well, that part's true. If I plug a 2 in, that'd be 3 over -1. Is that greater than 0? 2 over -1 is greater than 0?
Sorry, I thought you said 2.
Or 3 over -1? That's false. So the only parts that work in the domain are from -1 to +1. -1 to +1. Range. Because 0 is not a stopping point. 0 doesn't mess it up. 0 actually works. And then anything, if you plug in +1/2, it would work as well. But plug in +3/4, it works. Anything up to 1. You're finding these points right here on this number line that I'm finding come from the denominator set equal to 0 and the numerator set equal to 0. That's where I'm getting these numbers from. Anytime it's a rational expression that we're taking the log of, that's what you want to do. That's where I'm getting this -1, this +1, is from setting the numerator equal to 0 and setting the denominator equal to 0. And then I'm picking points to test out of that. All right. F of x, log base 2 of the absolute value of x. Taking the log of an absolute value. So if I set the absolute value of x greater than 0, it just can't be 0, right? So the domain goes from -infinity up to 0, and then from 0 positive infinity. Because if I put a negative number in there, the absolute value takes care of that negative, gets rid of it. So that's why Holly says it just can't be 0. And then the range what about log base 13 of the absolute value of x plus 2? A little bit more involved problem here. And then we're about to get to solve equations in a second, which is the fun part. So this one for the domain, what's going on? Is it? So this is how it's set up. Does anybody remember how to solve that from Algebra 1? Right? What the correct way of solving it is? I think Thomas is right. It can't be -2 for sure. It's x plus 2 is greater than 0, or x plus 2 is less than. Technically, it's supposed to be -0, but that doesn't exist. So we just know it's got to be greater than, right? So there's where, -2 is the. And technically, it's x is less than, not equal to, but less than -2 as well. So -2 is the thing that's going to get the absolute value equal to 0. So our domain, it's the same idea as the previous example, except for we got something else inside of there. So what's going to make the absolute value equal to 0? It's a -2. It does that. And then the range is kind of boring because it never changes. Oops. Because there's no such thing as -0. But you just got to know, okay, well, if this gets below 0, it's negative, but it's inside an absolute value. So that cancels out the negative part. So we just need to know, when is it going to be 0? When it's an absolute value in there. So when is it going to be 0 at -2 is really what we're looking for. All right, let's solve some equations. This is where we start using the things we know. So example R is log base 3 of 4x minus 7 is equal to 2. So here we have a log equation. And we don't have logs on both sides. We don't have, things happening that help us. If we had logs on both sides, then it makes it a little easier. But we don't. So what we want to think about is, how can I rearrange this problem so that it does make some sense and I don't have a log in it? So how could I rewrite that? 3 to the second power, equals 4x minus 7. So that's where, hey, we rewrote that logarithmic equation as an exponential equation. And now, what's 3 squared? 9. So we have 9 equals 4x minus 7. And that's, 7th grade math right there, right? And this is where we're like, oh, yeah, this is easy. And we get in a hurry and we screw up and make a mistake. No pressure or anything, but don't screw up.
Is this back to where we were at the beginning?
It's using that skill, yes. All right. Now we need to check that to make sure it works. Make sure it doesn't get what kind of number inside of the log. Negative. It doesn't. 4 plugged into 4x minus 7. 16 minus 7 is not negative. So
if you follow your number,
you got right. So it's possible you could have no solution.
So you always have to put
Yes, you always need to check your answers. Here's a pretty easy one. Log base x of 64 is equal to 2. Yeah. X squared. And then we can solve that by doing what? Square root. What was that? Plus or minus 8? It's okay if our base is a negative number. We can't have a negative that we're taking the log of. It's okay for the base to be negative, though.
But then you calculate in for x, you put positive and negative in it. You just work like that.
To check them?
Yeah.
Yeah, yes, yeah.
Make sure you get through.
Right.
So if we can check it with the calculator,
Because you need to know how to do the ones that won't work with it, that are not nice.
oh, let's do one of those.
All right, here's a different kind of one here. Uh-huh.
How come the x equals negative or positive 8? How come it can be a negative?
The base can be negative
Okay.
because we can raise a negative number to a power and it'd be okay. Because if I raise negative 8 to the second power, what's negative 8 squared? It's positive 64. So that works. And if I raise positive 8, I also get positive 64. So that's why the base can be negative, but we can never take the log of a negative. All right. So on this one, if we rewrote it as an exponential, we'd end up with 3 to the what? 3 to the 42nd equals 3 to the 6x. Yeah. So x would be 7. Now, here's the shortcut to that. Instead of having to rewrite it all like that, these cancel each other out and you just get 6x equals 3. But the log base 3 cancels out the base of the 3 here. That's a property of logs that we don't necessarily have to have, but it does work. It exists. It's kind of like, the property that says, 6 times 1 is 6 and 1 times 6 is 6. It really doesn't do anything fancy. It doesn't really help you a whole lot in the world. But it does exist. It does happen. Yeah. As the base here, yeah, they can cancel each other out. Yeah, so like a log base 4 would cancel a base 4 there. That's really is exactly how it is.
So that's why we ended up with 6x.
Yeah, that's how, here we did it with exponential because that's the way y'all said, which is absolutely correct, that it's 3 to the 42nd power is equal to 3 to the 6x. And we got that. But there's a shortcut that can happen that shoots you right here. But you skip that exponential step.
Why did you do 3 to the 42nd?
Because it's base, exponent, what it's equal to. Base, 3, exponent, 42. Rewriting it as an exponential like we did at the beginning. Let's do another one. Maybe it'll make sense. All right, I'm going to show you this one. And this is where we're kind of leading into those areas where we can do something with them. Dylan, I'm headed toward that direction. I want to show you this so that we can do one that doesn't. So let's solve this exponential. This is like what we did yesterday. How do we do that? Base to the 3. So that's 3 to the 4x equals 3 to the third. Now, yesterday we were just magically dropping the 3 that's the base. There's math that actually makes that happen. It's what cancels out a base of a 3? A log base 3. This is really what's happening. So x equals 3/4. That's really what we were doing. We just didn't say we were using a log to get rid of it. That's not as important on this type of problem as it is on this problem where you have 3 to the 5x is equal to 24. 24 can't be written as 3 to a power, right? So there's where the problem exists, that we can't do that with exponential stuff. So we could get rid of the base 3 though with the log base 3. That if I take the log base 3 of 3 to the 5x, I have to do the same thing to the other side. Well, on this side, what happens with the log base 3 and the 3? They cancel each other out, and we just get 5x over there. Insert some space eventually. So we have 5x is equal to log base 3 of 24. How do I get x by itself? Divide by 5. So here is our log base 3 of 24 is equal to 5. I can't break down 24 to be a 3 to a power, right? But I can't, that's an exact answer. And then here's where we use the calculator, Bill, and this is what you're asking. When can we use it? This is when you would use that we can get the decimal approximation for that using our calculator. And the way you want to do that, open up my calculator. I hadn't had it open because I would be tempted to use it. As we type in Jay, they need you in balance. So wake up and go with Miss Angela. She's out here waiting on you. All right, so to get the log base 3, you can hit math, and if you'll press the up arrow, you'll find log base right there. And it gives you. All right, so log base 3 of 24. That's one way to get the log base 3. And then I'm going to divide that by what?
Where did you press?
I hit math and the up arrow to get log base. Should be, yes.
Mine just says solve.
Above that.
Oh, there.
Yeah. All right. So you can do it that way. I'm fairly certain somebody's probably already figured out that you can press a different button like, what's it? Alpha F1, maybe? No. Alpha F2. Yeah, that'll get you there. Or you can press Alpha F and then the window button, and there it is. Find there. So it's about the same either way you get there to get that. So log base 3 of 24. We're getting that answer, and then we're dividing it by 5. So 0.579 for around to 3 decimal places. Nope. It won't make a fraction. If you hit fraction or math enter, it won't do it. It can't convert that to a fraction. It doesn't.
How do you get the 5x equals log base 3?
I took the log base 3 of each side to cancel out the base of the 3. To cancel out a base 3, you use a log base 3. To cancel out a base 5, you use a log base 5. Whatever the base is, you use the same log base to cancel it out. To cancel out an E as the base, you use
Natural log.
natural log. Yeah, log base E, natural log, same thing. That's what you want to do. All right. One more. 2 to the 3x plus 1 equals 15. Last one. So yeah, can't make the bases the same, so we're going to use log base 2 to get rid of that 2. So that cancels that, giving you 3x plus 1 is equal to log base 2 of 15. And then just get x by itself. So this is just a number. That's all that is. It's just a weird looking number. Okay? Subtract Subtract 1. No, it's like this is,
That's in parentheses.
yeah, that's like a parentheses type thing. So it's 3x equals log base 2 of 15 minus 1. And then divide everything by 3. So x equals log base 2 of 15 minus 1 over 3. And then you could get the decimal approximation for that with your calculator. Okay. All right. Before you go, page 445, 9 through 24, heck, 9 through 110. I'll break it down for you a little bit tomorrow of what you're doing on each section. Well, I break it down what you're doing in each individual section. I'll do that for you tomorrow. It's not a big deal. Okay.